In this video, I'm going to talk about the choice to use LAG versus ECMP in a service provider MPLS underlay. To discuss this, I've got this made-up scenario here in this diagram where we've got 3 PEs, and at peak times each evening, they're receiving 4 gigs of traffic each. And in this scenario, all traffic is just flowing in one direction, from the left to the right. I've abstracted out the rest of the network here with this little cloud. It's not important, the details of the topology from that on that side of the diagram. All that's important is that 12 gigs a second is coming during peak times from the left to the right, and all of these links in this diagram are 10 gig interfaces. We've got OSPF autocost reference bandwidth set up with set to 100 gig. So each of these 10 gigs has an automatic cost of 10. And the network engineering team has realized that, well, we've got 12 gigs peak each night going over these two 10 gig interfaces. So we've lost n+1 redundancy. If we lose one 10 gig, we're going to have 12 gigs trying to go over 10 gigs, and that's not good. We're going to be dropping traffic. So they're exploring upgrading capacity in this section of the network. And they don't really want to do 100 gig because their routers might not support it. They might have to upgrade their routers. The 100 gig circuit might be too expensive. And they don't have that much traffic to warrant that. So they say, well, let's just get another 10 gig in this path. So they go to a carrier and they find an offer for another 10 gig that's path diverse to this existing 10 gig that's between P1 and P2. And I should mention that these are long haul links. These are hundreds of miles. These are switched 10 gig circuits, like EPL style circuits, that this service provider is purchasing from another carrier. So they're purchasing this 10 gig, and they're wondering, should we do a lag between these two routers, or should we just do ECMP with two separate interfaces? And you might think at first glance that, well, it doesn't really matter, right? I mean, it's not a huge deal if you use one or the other, just whatever personal preferences. But I'm going to argue in this video that it does make a difference, a big difference, and you should use ECMP and not LAG in this situation. So just to kind of level set, this is a layer 3 MPLS underlay. This is not a layer 2 switched service provider network. In that case, it's probably using G8032, and redundant links, layer 2 links, would probably need lag so that they're not blocked by G8032. So this is not that. This is a routed layer 3 MPLS underlay. So whether you're using lag or ECMP, either way, traffic is going to be hashed over the two links, right? Either it's going to be hashed over the two links from an IP routing perspective or from the lag perspective. And the hashing is probably the same either way too. It's probably based on MPLS label because these routers are MPLS switching routers, and they are not looking past the MPLS header to do their forwarding. So in either way, a flow cannot achieve more than 10 gigs per second because these are two separate 10 gigs. So really the question just comes down to, do you want to abstract the two links away and have one logical link, or do you not? Do you want to have two separate links? And what I'm going to argue in this video is that the process of abstracting the links into one logical link with a lag comes at a price. And that price is that you lose visibility into the individual links from a failure detection and a troubleshooting perspective. So to start off this video, I did want to mention the trouble to set up a lag, like migrating to a lag and configuring the lag. That's my first point here. So right now, these are layer 3 interfaces on a physical link. So let's say the team decided, okay, we're going to do a lag on these. Well, they're going to have to convert that physical link to being a member of a lag. They're going to have to move all that config on the interface to the lag interface. They're going to have to probably take a maintenance window for this because it's going to be impacting. They're going to have to take the link out of service. They're going to have to move all traffic to this 10 gig while they do this. This is potentially error prone because they're going to have to look through their whole configuration, depending on what router this is, what vendor. Find all the places this interface is used and make sure to replace it with the lag interface, the logical interface. That is a lot of work. Error prone, needs a maintenance window. With ECMP, you don't have to do any of that. You just, as you set up this new interface, it's just a brand new separate interface. Put a layer 3 addresses on it, put it in your IGP. You can put it in your IGP with a high cost at first, so that's not used. You can do some testing over it. Once you put it in your IGP, you can even do some traffic engineering paths to put a little bit of traffic over it, test it out, that sort of thing. With lag, you can't do that. Either the new interface is either in the bundle or it's not. You don't have control over how much traffic you're pushing through it. So that's some difficulty with lag. I've seen some providers might do this thing where if they use lags in their underlay, they could just configure everything as a lag. So anything that's even just a single link between routers, they're going to make it a lag and have it be a single link lag. I personally don't like this. I find it confusing and kind of ugly because when you look at, you're like, well, why is this a lag? Did this used to have more interfaces in it and they got decommissioned and nobody changed this over to just a regular layer 3 interface on the physical interface? And LACP doesn't give you any benefits over just doing BFD with a layer 3 interface in terms of like failure detection and stuff. So I don't like doing it that way, but it is an option because then if everything's a lag, to add in this situation, if sorry about that, if this is a lag already, then in this diagram, all you have to do is just add this single interface to the lag, and that's it. So my next point is ease of troubleshooting. So with using a lag, because you've abstracted the multiple member links away into a logical link, you've lost some of the tools that you have to individually test, troubleshoot, monitor those individual links. So let's say that the team did decide to go with a lag. They went through all the configuration overhead of changing that interface to a lag. Things are going fine for a few months, but then they get a report of packet loss to these PEs. And they've narrowed down the problem to this lag, but now they don't know which link is having the loss. Maybe these are two separate carriers. So they want to be careful. They don't want to open a ticket with the carrier and say, hey, I've got loss on this. And they say, well, we spent all these resources testing that link and no, there's no loss. So now we're going to charge you for that. They want to know which link has the loss. With lag, this is going to be tricky to do. With ECMP, this is easy. You can even do something so quick and simple as going into P1, ping.2, repeat 1,000, is there any loss? Now ping.10, repeat 1,000, is there any loss? If there's loss on one of those links, now immediately you know which link has the loss. You can open a ticket with the carrier. You can choose to drain traffic off that link if you want to, that sort of thing. With lag, how do you test individual links? You can't because you've lost that ability by abstracting the links into a logical one. So one thing you can do, I guess, is just shut down links. But let's say you shut down the first link, but that was actually a good link. Now you're just have more loss, and hopefully and then you see loss, and then now you have to bring that other link back up, shut down that link, and then make sure there's no loss on the other link. It's not as graceful. It's intrusive to do that. I think it's a disadvantage of doing lag. Also, because you've abstracted the links, you can't use Ethernet OEM tools. Like you can't run CFM probes every 60 seconds and just have that continuously run, and maybe you graph that in an NMS, that sort of thing. With ECMP, that's very easy. You've got two separate CFM probes going for these two separate links. You can monitor loss and that sort of thing from an Ethernet perspective. With the lag, you've abstracted the links. So you've only got one OEM probe that's going over those links. You don't know which link it's hashed over. It's not all that useful because you're only monitoring one of those two links. So next, let's talk about the failure detection. And this is really the main point where lags can become very troublesome. And it's very tricky because this is a service provider environment, IGP running MPLS. Of course, we're just going to use BFD over our IGP, OSPF or ISIS. So with how I was talking about migrating that link to the lag, you might just think, okay, well, I'm just going to replace where I had the physical interface with the lag interface, just one for one, and everything will be fine. I'm running BFD over it just like I was before. But it might not work like you think it does, and you put yourself at risk for this nightmare issue where you might run BFD on the lag, but you've only got one BFD session over that lag. So that BFD session is only hashed over one link. If the other link fails, BFD isn't detecting it, and LACP will take 90 seconds to detect it by default because the LACP DUs run by default every 30 seconds. And if 3 are missed, then it knows, okay, that link is not available anymore from LACP perspective. Take that link out of the bundle. So just replacing the config one for one and just leaving everything at the defaults, you've opened yourself up to this scenario where you can have blackholing of traffic for 90 seconds. And that's just very customer impacting. And to kind of show this, on iOS XR, doing what I said is called BFD over bundle. They abbreviate it BOD. And, oh no, I'm sorry, this is BFD over logical bundle, abbreviated BLD. And in this scenario, you just put the bundle under the IGP like normal, enable BFD on it, and you're done. But this is just one BFD session hash over the bundle, because again, you've abstracted the underlying physical links into one logical link. So from IGP's perspective, oh, this is just a regular link, I'm just running one BFD session over it. It doesn't know that you really care about individual members of the link going down. So there is an option for running BFD over multiple or every single member interface in the bundle, and that's called micro BFD. There's an RFC for this, RFC 7130, called BFD on lag interfaces, that so it's standardized. The only problem with it is that it doesn't support BFD echoes. And I believe the reason is that it needs to use BFD control packets, because there's probably some like identifier that determines like which member of the link this BFD session is on. So by using that identifier, you can the routers can determine which BFD session belongs to which interface, that sort of thing. So you don't have the option of just using BFD echoes, which are offloaded into hardware. So there's a downside to this. And to make this even more complicated with Cisco, they call BFD over the bundles BOB, and that's where you're running micro BFD. And you have to configure BFD under the bundle itself. You don't configure this under the IGP. In this situation, the bundle manager application is the BFD client. The IGP is not the BFD client. So if we go back to this situation, in this situation, ISIS is the BFD client. ISIS registers BFD and says, okay, BFD, run BFD on this bundle ether. Let me know when it goes down. When it goes down, I'll bring it down in the IGP. In this situation, the bundle manager process registers with BFD and says, hey, BFD, run BFD under all of my member interfaces in this bundle and let me know when they go down. When they go down, I'll take them down from an LACP perspective. If all of them go down, the bundle itself is just down, just like normal interface goes down from the IGP perspective. So in this case, the IGP has nothing to do with BFD on the bundle. There's this feature called coexistence between BFD over bundle and BFD over logical bundle, where you do both at the same time. This article talks about how BFD over bundle, where you enable it on the physical bundle, is micro BFD. It doesn't provide a true layer 3 check, and it's also not supported on sub interfaces. Whereas BFD over logical bundle has that problem we're talking about, where it's cannot reliably detect individual member links. So really, this problem, to expand upon it even more, it's a problem either way. Like, let's say BFD is running over the logical bundle, but it's on the top link. If the bottom link goes down, traffic's going over for 90 seconds and you don't know. Let's say this is during peak times when there's 12 gigs a second of traffic, and BFD is running over the top link, and the top link goes down. Well, now BFD thinks the entire lag is down. So it brings the entire lag down from IGP perspective, and all 12 gigs is going over this 10 gig link at the bottom. Traffic is getting dropped, even though there's a good 10 gig interface in this bundle before. So that's what this article is talking about. And it says, well, if you want to do this coexistence thing, you can have this command here to do both at the same time. So the whole point of this is that it's possible to do BFD over the bundle, over a lag, but it's just kind of complicated, and you have to really be aware of how it works. You might just think, oh, well, I've got BFD on my bundle like normal under the IGP, I'm done. You're not really done. You're not protected from these outage situations. You're not running BFD per member link. So you're going to have to do some research into if your equipment supports micro BFD. Are there any caveats with it? How do you enable it? All that sort of stuff. With the ECMP, there's no difference. It's just BFD like normal. Don't worry about all this micro BFD stuff, and it can be hashed. It can be done in hardware. It's just, I think, so much easier. So we've talked about the issues with migrating to a bundle or a lag, the issues with troubleshooting the member links of the lag, the issues with detecting failure of member links in the lag. So now let's go over why would you want to use a lag in the first place? Are there any advantages? Yes, there are a few advantages. To me, they're small enough to not warrant using a lag in this situation. But an advantage you could say is that it uses less IP address space. With a lag, you've got this 1/30 or /31 in the lag, no matter how many members are in the bundle. With ECMP, you're using IP address space for every single link. In my pretend scenario, that doesn't matter because we're doing RFC 1918 addresses in the underlay, because we're doing all of our services as VPNs, MPLS VPNs. So the internet isn't a VRF. If you were doing the internet in the default table and you weren't disabling IPTTL to MPLS TTL propagation and stuff, so these links were visible in trace routes, you should probably use public addresses on these. It's kind of best practice. So you're going to be using up public address space the more interfaces you have, whereas from the lag, you just use up less public address space. So that's one advantage. Another advantage is that from the IGP's perspective, there's less overhead to the lag. It uses up less memory. There's less entries. If a individual member link goes down, it doesn't notify the IGP. It doesn't flood the event. It's just contained within the lag itself on those routers. The graph is smaller because there's only one link between these routers versus multiple links between the routers. But again, that's a trade-off because the more with having the multiple links between the routers and the IGP, it gives you the ability to do traffic engineering over those individual links. Whereas right now with this bundle here, I can't traffic engineer paths, MPLS traffic engineering I'm talking about, on these individual links. Whereas with ECMP, if you're using SR, these have separate adjacency SIDs. With RCPTE, there's a separate links that you can traffic engineer paths over. So it gives you that control. In my opinion, this savings of a little bit of memory in the IGP and stuff is not worth all these headaches with the lag. Any other advantages with lag? I guess if you like just being able to manage this one link, this one logical link, if you want to take all of these links out of service, with a lag, you just take that one link. With the ECMP, you have to remember that there's multiple links. I think that's about it. And then let's say that you decide you do want to use lag, you like those advantages. What should you watch out for so that you don't have issues with using a lag in this situation? So the first thing is that you should enable fast timers if your hardware supports it, if you determine that it's not going to cause CPU issues and stuff. With LACP, your only options are either slow timers, 30 seconds, or fast timers, 1 second. No in between. It's a little bit analogous to running OSPF 1 second hellos. That's why we use BFD, but to not do that. But if you're going to use lag, I would feel more comfortable using fast timers because if for some reason I have to rely on LACP to determine that a link is not usable, I want it to detect in 3 seconds and not 90 seconds. I'm talking about a situation where the micro BFD has some issue. It's not running like you thought it was. Which brings me to the next point that if you're going to use lag in this situation, use micro BFD, do some research, understand how it works, understand how it's implemented in your vendor equipment, all that sort of thing. Test it out to make sure it's actually doing what you think it's doing. What else? I guess accept, the configuration overhead of changing to a bundle and all that sort of stuff. Make sure you're not making issues as you're changing the config. Have a plan for how you're going to troubleshoot individual members of the lag. Are you just going to shut down links and test like that? Just something to think about and be aware of as you set up the lag. Let's see. If you're going to do ECMP, is there anything you have to be careful of? Not really, because this is just another layer 3 link, just like you're using. Of everything, fault detection, troubleshooting, configuration, everything's normal. In my opinion, this is going to be easier for operations teams then because they don't have this layer of the lag they have to deal with. This also reminds me that with the lag, you're running LACP as another process that can crash, have bugs. ECMP is more simple in that way. In my opinion, you've got that layer of LACP gone. So with ECMP, I guess the only thing to be aware of is how the cost works and be aware of how traffic is going to move from an IGP perspective. Because there's a difference with IGP costs from ECMP versus lag in this situation because we're using OSPF with auto cost reference bandwidth. With lag, this is a 20 gig interface because it's an aggregate of the bandwidth of both the links. So the cost is going to be 5 here. And now all traffic is going to go in this path from P1 to P2 to PE3. No traffic is going to go down in this path. This link is going to be completely unused. Maybe that's okay with you. Maybe that's what you want. But if you want to share traffic on this path, you have to manually change this to a cost of 10. And now you've got one-to-one traffic. So now you can't really support more than 10 gigs of traffic on this lag because you can't support more than 10 gigs of traffic on this lag. So, this is just something to be aware of. In this situation, you can't do something like 2-to-1 hashing where you've got 1/3 of traffic on this link because what would you set your cost to achieve that on this lag? OSPF can't do unequal cost multipath. So you're kind of stuck there with either all traffic going over here or 1-to-1 link sharing. With ECMP, you have more of an option because you can do 2-to-1. You can have 1/3 of traffic going down here because in this case, by default, it's 3 ECMP paths for P1 to PE3, 2 from PE2 and 2 via P3. So if you don't want this, if you want all your traffic to use these 2 links and only use this in case of backup, well, then you just have to increase the cost of this link manually or something like that. So yeah, ECMP and lag, I think neither one has an advantage when it compared to this topic of IGP costs. It's all just a matter of what you're trying to achieve, and just be aware of how the auto cost is going to work because the lag is aggregate of the bandwidth. So you might just have to manually set costs. So I think that covers everything I wanted to discuss in this video. I hope it's been interesting, and if you thought of anything I missed in this video in terms of reasons to use lag over ECMP, please let me know. I'd be interested in hearing. And thanks for your time and for watching.